Thanks a lot for the nice introduction. I'm actually really glad to have this opportunity to introduce in few slides SleePyLand. SleePyLand is a small project recently founded by the Swiss Open Research Data Grants program by Swiss universities. And in SleePyLand, the idea is to develop a Python library to analyze the large amount of NSRR sleep data, exploiting deep learning algorithms. So what do we mean with analyze? So the first step that we need to do in SleePyLand is to be able to manage, pre-process, extract overall sleep patterns, sleep parameters, and statistics from the large amount of NSRR sleep recordings. Now, a little spoiler, to do that in these projects, we are going to exploit, of course, Luna. That is a really wonderful, I would say, tool set that already is able to do all these stuff. So to manage, process data, and so all we need to do here is to just build a bridge between Luna and our Python-based library. The most important part in SleePyLand, and here comes the main goal, is to actually provide for each sleep recording a sleep report via an automatically assembled deep learning sleep scoring system. So basically, SleePyLand will be an open source repository benchmarking all the recently proposed high-performing deep learning scoring algorithms. So all these algorithms will be fairly retrained, and then I'm gonna explain what I mean with fairly, and evaluated on the same data sets. So at the end, the system will then be able to output the ensemble sleep scoring predictions. Now, why SleePyLand? What is the problem to solve? Actually, to date, I have to say that we have a lot of sleep scoring algorithms. Here, I'm just reporting a few of them, deep learning based and exploiting actually signals from the brain. The point is that all these algorithms comes with some limitations. I will say the majority of them have been trained and evaluated on low quality or poor data, so meaning the data were not enough and not heterogeneous. And only few of these algorithms have been evaluated on out-of-domain data. So I will say resulting in poor generalizability on the different hardware or different sleep labs. So different patients with different sleep disorders and so on. Here, I'm just highlighting the recently proposed algorithms that have been trained and evaluated on many recordings, up to 30K PSGs. But still, also on these recordings, it's really hard to compare these architectures. So the point is that the problem is that all these algorithms are not directly comparable. So we cannot fairly, they've been not fairly trained, validated, and tested on the same set of data. So, and here comes the main goal of SleePyLand. Here I'm sharing with you the journey that we're gonna go through with SleePyLand in the 2024. So it's a one-year project and is divided basically in two parts. So in the first part package, we're gonna exploit some together with Professor Sean Purcell, some Python bindings for Luna to be able to then manage and analyze all the data from the NSRR. Then in the second part, I will say the most important part, here we are gonna retrain from scratch specific selected deep learning algorithms to be able then to ensemble their knowledge and so to output the prediction, the ensemble prediction. And who knows, maybe we're gonna then merge this SleePyLand knowledge with some automated sleep scoring algorithms like SOAP or POPs that are already implemented, have been already implemented in Luna. And again, the aim will be to then integrate SleePyLand in the Luna software. So these are the data sets that we're planning to exploit, the NSRR data sets. And I will say this is really a huge amount of knowledge and data that we can benefit, actually, because here we have up to 30K subjects from 16 different cohorts. And it will be really beneficial for the algorithms itself because we can train on all these let's say set of data that are really heterogeneous. So okay, I'm going to focus on the second part, so the second word package. Because here I want to share with you overall which kind of algorithms we would like to include. This is the list of, let's say, the top algorithms, deep learning based, that we are planning to exploit. So please here, maybe if you can give some hints, or if you know some let's say architectures that have been trained on a huge amount of data, or that have been shown to be really high performing, I would love to hear from you. So please just text me. The point here is that when we are going to try to exploit all these algorithms, we're going to face some challenges. And here I'm just reporting two of them. One challenge is related to the data themselves. So in a way, we have to feed this data on all these algorithms. And as you can imagine, all these algorithms have been built over the years on different data sets. So it will be really hard to I mean, we have to think on some methodologies, or on how, for example, split the data in the different sets, train, valid, and test, but not only considering, for example, the sleep stages, because we know that we have an imbalanced data sets, but even considering maybe the heterogeneity that we're going to have in these different set of data, and how these heterogeneity are going to have an impact on all these algorithms. Another issue that we have to solve is that all these models have different capacity, of course. So some of these models are really small because they have been evaluated and validated on small data sets. And so at that point, I will mention that if we're going to train these algorithms on a huge amount of data, the capacity will be insufficient. These models can underfit. So these are this is one of the main, I think, issue that we have to look at and solve. So I'm going to leave you with these workflow summarizing the whole project. So as you can see, we're going to start from the NSRR data. We're going to find a way to process all this data and harmonize the data to let them be ready to give input to all these deep learning based scoring algorithms that we have selected and we will select. And at the end, the idea is to, of course, benchmark of these algorithms on testing data, but also on out-of-domain data. Then try to, give a sort of ranking of these algorithms, and maybe ensemble the predictions. So given the top 3 algorithms, try to output a hypnogram and a hypnodensity graph with all the transitions and probability on the sleep stages given by different models. It's like having different, let's say, sleep scorers at that point. So I would like to thank my biomedical signal processing group from Switzerland, Medit at SUPSI, and all the university cooperating with us in sleep projects. And I would like to thank you all for your attention, and I'm open to questions.
What channels do you anticipate using, EEG only or others?
Basically, we will start to use exploit EEG, but we have to consider that different architecture are using also other channels. So architecture that I've also mentioned. So of course, we have to exploit these architecture in their full power, let's say. So basically only EEG, but I would of course add EOG and EMG as indicated by the ASM when necessary. So depending on the architecture.
Do you intend on deploying these models in real time on novel incoming data sets?
I'm sorry, can you repeat the question?
Do you intend on deploying these models in real time on novel incoming data sets?
Yeah, this will be really a good application. Actually, there are some models that are really that are good enough to be explored in a real time, so in a real time case scenario. Some others are a little bit heavy, but yeah, we may think to select a subset of these models to be deployed in this way for sure.
I see. And will you be having normal healthy sleepers or a mix of clinically relevant data sets as well?
No, it's not only about healthy, but it should be mixed. And this is where actually I also mentioned one of the challenge will be to also try to balance this data when training these algorithms with this huge amount of data, but balance this data not only based on the sleep stages, so the classes that we want to predict, but also balance the data based on the demographic, for example, information from the patients and also disorders and so on. So we have to be sure to that the model are learning from the an heterogeneous distribution, let's say, to then be able to generalize on all the other data sets.